right, let's kick off. It's time. So thanks everyone for joining. We are hosting this webinar to share a couple of new ideas and also new products at Lynx and some existing products with new features. And we are gonna have two topics. And one of the topic is gonna be to use the graph analytics feature about LynxKite, which is one of our graph AI tool, and show a simulation and also with real data on some of the COVID-19 coronavirus use case, which is unfortunately reshaping the world day by day. And then the second part of the presentation is gonna be by Cylynx and by Timothy, and he's gonna show also a graph analytics use case, which is more closer to blockchain or financial transaction type investigation data, and also slightly more technical in the nature of building up certain graph analytics use cases. So with the first one, I'm gonna try to pass the presentation to Zoltan, one of our senior data scientists, and he's gonna show this together with Gabor, who is our Chief Innovation Officer. And it's going to be also just about the simulation first with any public data, and then it's going to be expanded with potential use of telco data in the second part of the presentation. So with that, Zoltan, please try to take over.
Okay, thank you.
All right.
Can you see my screen?
Not yet.
Okay, I think you can see it now, right?
Yes.
Okay, perfect. So, hello everybody. My name is Zoltan, and I'm gonna do the first half of the presentation on COVID-19 spread analysis. First, I would like to talk about the COVID-19 in general, in a nutshell. After that, a little bit about the publicly available data. And after that, I will go into the visualization of the spreading, and I would like to give you some critical insights about the COVID-19. So in a nutshell, the new coronavirus, also known as Wuhan virus, novel coronavirus COVID-19, was first encountered in Wuhan in China in December of 2019. As of yesterday, it was infected by almost 90,000 people around the globe, and it is responsible for approximately 3,000 deaths. Some of the symptoms might like pneumonia, coughing, fever, or even organ failures. Let's look into
let you know there is a background noise coming, so in case anyone else is here, you can ask not to hear the background.
Probably it's not coming from me because I'm sitting in an isolated room.
Okay. So anyone, please, if you don't speak or trying to, maybe it's Rob Childs. I'm gonna mute you. But, yeah.
Okay.
All right. So, yeah.
Okay. My first chart is about the spreading of the virus. Here you can see 3 different cases. For person A, he was infected in T0. After that, there comes an incubation period in which he is not able to infect anybody else. Basically, the virus develops in his body. After a while, the person shows some kind of symptoms, and then he starts infecting other people, like B and C in this case. After a while, he will be isolated, and after the isolation, he will no longer be able to infect other people. If you look into the person B, he is infected, and he's basically traced and caught during the incubation period of the virus. So before he shows the symptoms, he will be put into quarantine. So the chain of the spreading is broken here. Meanwhile, for person C, as he is not traced, unfortunately, he will be able to infect more and more people. And also there's a debate whether he can infect people during the incubation period or not. This problem can be easily represented as a graph, as you can see it on the left side of the chart. Let's move on to the next slide. Here in this, with this outbreak, we've got important actionable factors and also less actionable conditions. The first one is, the first important actionable factor is that the initial cases should be diagnosed when they're in the early stage, as only a small subset of people are infected. The onset to the isolation should be also minimized, thus preventing the further infection of other people. And preferably, about 90% of the contacts should be traced. That would be the best. There are other less actionable conditions. For example, the spreading factor of the virus, depending on where the people live or the health condition. The spreading factor can be, is ranging between 1.5 and 3.5. It means that one people can infect 1.5 and 3.5 people. And also the transmission before the symptoms can be detected is still in debate whether it happens or not. The spreading of the virus globally. The first reported case was in China in the late of December. And as of today, approximately 76 countries are in this one. During our analysis, we would like to focus on Singapore only. And as of yesterday, 110 confirmed cases were reported. And initially, this part was the highest in the region. And with the help of the graph analytics, we actually hope to bring some valuable insights on how the virus spreads across the countries over the globe. And for this one, we are using LynxKite, our proprietary tool for visualization. For the first use case, for the first analysis, we have downloaded publicly available data. And we're going to be visualizing the spread of the virus. Meanwhile, for the second one, it's a hypothetical scenario on Telco data. And now I'm going to switch to the interface of LynxKite. And this is my first use case. I have created actually 2 CSV files and imported the patients, the people, and also the links between them, and created a graph. So now, if you look into my output, here you can see that the blue dots represent the people. Meanwhile, the gray dots represent the places where the infected people met. I've created a slider for this chart, which is linked with the date of confirmed infectation. So it means that if I'm using the slider and pulling it to the right, more and more vertices will appear on map, as you can see. And this represents as we are moving forward in time. The interesting thing is that if I pull this slider to the left side, you can only see a couple of cases, and the label for the vertices is the citizenship of each people. So in the early stage, you can actually see that most of the people are from China, probably from Wuhan, the most infected province. And these are the imported cases. So probably these people just went back to China and imported the infection. And as I'm pulling it to the right side, a couple of people, a couple of infections, the single appear as they are Singaporean citizens. So this means that that the disease are now spreading within the community. And if I'm actually pulling it to the right, you can see that now the majority of the vertices are Singaporeans. Okay, the next one is we have extended the publicly available data with communities or places where most of the people met with each other, and trying to find the largest communities. And here you can see a bipartite graph where the left side of the image shows the map of Singapore and also the people and their citizenships. Meanwhile, the right side of the image shows the communities where most of the people are met. I have limited the number of the communities to 6 because otherwise it would be pretty huge, unreadable chart. So now here you can see that the biggest one is the Grace Assembly of God, which is a church close to Tanglin in Singapore. The next one, if I move on to my next analysis, here is basically the same. We have it's the same workspace. We have just extended it with PageRank computation. PageRank, in a nutshell, is basically it reflects the likelihood that a random walk will lead into a specific vertex in a graph. So in this case, we did a PageRank calculation with 5. So we wanted to see that which are the most infectious locations within Singapore. So we also had to manually add broader locations to the home or the visited places of the infected people. And then we calculated their PageRank. And here you can see basically the output of it. So these are, according to our analysis, these are the most infectious places. And what is actually not so surprising, that the biggest one is Tanglin, as you can see it on the bottom right of the image. And this one corresponds with the previous one as the Grace Assembly of God church is exactly at Tanglin. We also created a chart where we are showing the super spreaders for each location. So, for example, medical response teams can focus on those kind of people to prevent further spreading of the virus. Okay, now I will go back to my my slides. So we can say that as an interim summary, that data of the public transportation, for example, such as LRT, MRT, or even buses, would be pretty useful to estimate the expected growth of the virus. And also we can use Telco network data to help to discover who might be infected, because if we know the network of the infected people, we can also discover their networks even more easily. And now I would like to give the word to Gabor.
Yeah, and just time while you're doing that, if anyone will have question, like we want to add that rather in the chat box and then answer them all of that towards the end, after also Timothy shown his own section. And now, Gabor, please go ahead to take over the screen.
Yeah, thank you very much. So I'm sharing my screen. Hopefully you're able to see that. So this is the same LynxKite tool what Zoltan already showed to you. I have two streams line here. The first one is exactly the same data what Zoltan has analyzed earlier, and the second one is a little expansion of the analysis with some hypothetical telecom data sets. So I'm not going to explain all the steps what I had did in the past, but I'm going to just jump to the visualization. First, I'm going to show you the same visualization what Zoltan did earlier. The only difference is I decided to show you not on the map, because on the map, like, things are on the top of each other and they cover, the vertices are covered each other. So we start on day 23, where Singapore discovered the first case, and then we slowly go to the further days. That we have the second case, and we have the locations visited by, actually the third case, and the locations which were visited by these patients. The interesting thing is that first you can see the three cases, they are separate from each other. So you can see one component here of the graph and another component here on the graph. And we have to wait quite a few days and quite a few more infections to see what could have been the common link in between them. So you can see we are already at day 27, and furthermore, infections have been discovered in Singapore, all of them coming from China. And I think we should wait until day 33. Oops, I was a bit too fast. To see the first case, which is a Singaporean case. And interestingly, this case is going to be the one which is connecting these few Wuhan cases with the original graphs. So that case, that Singapore case, can be an interesting point of the infection. First imported case, probably the first imported case here. And just the next day, just the very next day, there are a few more infections very close, very connected to this initial Singapore cases has been appeared, and then I can go through and see how the infection went forward. And because I'm not projecting it on a map, I think it's more easy. It's slightly more easy to follow what was happening and how these things are connected. But what is going to be super exciting for me is this first case. So let me just put it on the map, and while I'm putting on the map, I'm just going to do slightly different visualizations. I'm going to put it on the map, so I'm going to use the positions as geo coordinates, and instead of the citizenship, instead of the from, which was the label, I'm going to put the case number. I want to identify this case number in the visualization, so I just did this slide changes. And everything is projected on the map. And remember, I want to find my made a mistake. So sorry. Label should be case number. Yes. And I'm searching for my first Singapore case. It's here. It's case 19. We have identified this case near Kitmera. And then we can see, if we go to the further cases, some more cases are going to appear probably in the same household of this case, for these 4 cases. And these are the cases which are strongly connected together with each other in this map. And like, of course, if I continue, I will find all the other cases on the map. But okay, let me just focus more on this case 19. So let's imagine that I can have an access to the core data record, the CDRs, for this patient 19. And let's imagine that I can load it into this graph analysis tool, and with the help of the location with the past CDRs, I will be able to identify or trace back the moments or the important points and the possible potentially infected cases or further infections of this patient. So I'm going to simulate a telco data stream, a telco database. And again, without too much details, I'm just going to click to the visualization to see how can we trace it with the tool itself. So yeah, here I am. Here I identified my case 19, close to Gitmera. And the first thing what I want to identify is in the last 14 days, which locations this customer visited. So which set hours are those set hours where this customer or this patient was using in the past 14 days. So let me just click to that visualization, and I'm going to change the center instead of case 19 to the cell towers. I'm interested in the cell towers, and I have randomly selected 300 cell towers. And the reason why I selected randomly 300 is because probably there are much more in the last 14 days, especially if this customer, if this patient is very mobile. So you will be able to see lots of cell towers in different locations in Singapore, and each of these locations there are other I did a few filtering, so I only consider those locations where this patient has spent more than 15 minutes, because we assume that at least 15 minutes is required for the infection. So let's see that how many other customers of Telco data is connected to these locations at the very moment when my infected case 19 was there. And again, here we would see hundreds of thousands of customers. Here I just selected a few hundred to kill the full visualization. But still, you can expect that your chart is going to be super messy with all this data. So for example, here is one patient, here is another patient, here is another patient, and immediately you can see those locations where this customer was co-occurring with our initial case 19 patient. So let's make this chart a little bit more easy to see. So I'm going to take out first these connections, and I'm going to count at each location how many co-occurring customers do I see. For that, I created this diggery. I'm going to use the label to show this diggery, and I go back to Bukit Merah, and I go to that, for example, this location, this tower, where I see that there were 4 other patients or clients collocated, represented in the very same time as our initial case 19 appeared. I would like to analyze a little bit further this location. So what I'm going to do is again put back the connections, put back all the connections, and after putting back all the connections, I'm going to just select only on this location. I'm going to say that please use only this location for the further analysis. And what I see, is that I can find 1, 2, 3, and 4 connections for customers or patients who have visited this location at the very same time as our patient 19. But I can go further, so I can check this guy and I can add it to the center, and I will see that, oh, by the way, this guy here has also visited this location and this location and this location at the very same time as my patient 19. Maybe the visualization is going to be even nicer if I just use the name of the location and maybe the color, or is it a cell site or is it a patient? And of course I have to redo my selection. Obviously I forgot where I pin, which I think it was here, this one. Yeah, boutique meta center. So I'm going to select this guy, set as the only center, and then find this guy, add the centers, and I identify the second one was co-occurring Lenko in Depot Road, Denford, Jalan Selatan, and even out in Tampines. So initially, if you start with this analysis, you would probably identify hundreds of thousands of potential collocations, random collocation with your initial patient. But as you go and identify further collocations, like this cannot be random. These two patients, these two customers must know each other because they are appearing so many different places, so many times during the last 14 days. This just cannot be random. So it can be a good trace to analyze further this one. And with this technique, it is possible to reduce the several hundreds of thousands of potential co-occurrence with our initial infecting patient to a few hundreds or sometimes even just a few dozens with the help of the data. So with this, I would like to finish this presentation. I'm going to stop sharing, and I think we can go to the next part of the presentation, which is about treating really large graphs, like this graph would be.
Yeah, and just as a conclusion to this on Gabor, obviously what we have done here depends on the regulatory environment and privacy and all of these frameworks. So this can be done in a very hashed way, but the output of this can be that for any single sort of ID, whether it's hashed or not, if it's needed to be, it can be listed that over the last 14 days, which are the other IDs that might be at the highest risk in terms of the tracing, and just identify those IDs also who were exposed to this location. And as the research shows, that as long as you can catch this virus when you don't have more than 100 patients early on, like that's almost the key to tackle it very early on or not. And that the other condition was whether you can trace at least 60% of all the contacts. If you wait even 2 weeks or 1 week, like as it happened in Italy, you can see that like by that time when it's 1,000, it's kind of too late, but there's still a couple of countries still very low digits, and whatever toolkits you are using or the Telco or the health authorities using, this is definitely something that can help their work. All right, so we can now pass over to Tim.
Right, so let me start my presentation. I'll be sharing a little bit about Lynx, which is, present. So I'll share a little bit about Lynx, which is our product that we created around the blockchain, primarily for the focus of analytics and forensics. So this involves building a solution that is suited for very large transactions graphs. And the main reason why we came up with this is that we see increasing use of blockchain in the enterprise space today. So a lot of executives believe that there's a compelling case for blockchain technology nowadays. And we are seeing increased use case, for example, in trade finance, as well as even within the telco area, where we see it being used for international settlements, for example, in the IBAN project, right? So while blockchain is a great enabler and a ground source of truth, we believe that the next step to unlock value for the blockchain is to actually derive analytics insight and to connect it more directly with whatever business requirements that might be. So in fact, a survey from Deloitte in 2019 found that the main issues facing blockchain systems is really on the implementation, regulatory issues, cybersecurity, security threats, lack of in-house capabilities, skills, and understanding. I think it still takes quite a bit of time for it to translate from actual blockchain POCs to on-the-ground initiatives and how it can actually link up with actual like business value. So what we try to do in Cylynx, or our product Lynx, is to actually derive and pre-calculate certain kinds of information that a business might find useful and to present it in a readily accessible manner. So let me introduce Lynx. It's a transaction risk monitoring platform that we have come up, and it supports very large-scale graph analysis. So let me show you the product demo. So this is our website, blocklinks.cylynx.io. Anyone can go in, create an account, and test it out. Currently, it supports the Ethereum chain, so there is more than 100 million addresses and 300 million transactions on the public ledger. So feel free to test it out. You can really query for anything, and it's really meant to give a sense of how a product would then scale to like enterprise environments as well as other larger chains. Ethereum, by the way, is like the second largest chain currently already. But our product is meant to scale to more than like 10 times or 100 times the node or transaction size. So what we aim to do with BlockLynx is provide like compliance and monitoring services for any transactions that go on the chain. So for example, in the risk scoring panel, you can enter a transaction hash and retrieve information easily about it. Or you can integrate your backend API system with our services and only get alert when we flag a particular entity as a very high risk entity. And what I mean by high risk entity here is something that can be customizable, can be customized by the business side of things. For the public chains and what we deal with, when we deal with a lot of regulators and exchanges, one area that they are concerned with is, for example, whether someone's interacting with any hack or scam funds or any suspicious entities, especially for the purposes of money laundering. But we can also include this to look at, for example, anomaly detection or cybersecurity frauds. Right? So the goal of the presentation is to share with you a little bit about the methodology which we can do very large-scale calculations or large amount of blockchain transactions, transaction logs. And this gives you a sense of the kind of reports that we can produce. So what we allow is to convert the blockchain logs into actionable information. For example, you can search on information about a particular entity or any particular address hash from any time period, and our system will aggregate this information to produce the report for you. So one example I can show you, for example, you can just go in and try yourself because everything is working and it's a full proper demo. So we look at Binance. Binance is the largest exchange in the world. We can look at Binance, for example, in the past 3 months and generate a new report for it. So we're then able to see the proportion of funds that we can trace from various sources. Of course, most of it will come from exchanges themselves, but there might be other interesting sources of funds. For example, we find that 4.3% of funds are coming from mixer sources. So these are normally sources that people use to avoid tracing and might be a source of concern for AML regulators. 2% of the funds are coming from mining sources, and so on. So, and another interesting thing is we can show the fund breakdown by time. So in this chart over here, what we noticed actually when we took a look at this chart is there was an influx of money coming in from 6 January to 13 January during that week. Actually, we did some investigations on it and we found that it could be traced to the North Korea hack. So North Korea actually hacked Upbit, which is a South Korean exchange. And what frequently happens because it's so easy to create multiple wallets on the blockchain is people tend to create these wallets and move money around. And these wallets are so-called anonymous.
Hello.
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 Sorry, if someone's on the other side, you mind muting yourself?
Same day, busy with the proposal, same.
So, hello, can you mute yourself? Yeah, background.
I muted, I didn't understand, but yeah. So if they have a question, maybe they can ask in the chat.
Yep, or we can have questions at the end of the presentation. Yeah, so let me continue. So we actually trace these funds down to Upbit, which is a North Korean hack of South Korean exchange. So let me show you how we do it. This is actually large value as well, like $400,000. So when we receive a transaction with very high risk, we can then visualize it in our investigative panel over here. So this gives you a time series view of all the transactions in the blockchain. And I think with this approach, we're able to visualize and show more than 300 million transactions that Of course, if you visualize 300 million transactions, oftentimes it's not really useful because you can't really make sense out of the 300 million dots on your computer or 300 million lines on your computer. What you try to do is to provide a tool and solution to give you the relevant information and present it to you such that you can actively make sense of the information and take business actions out of it. So what typically happens is that someone finds that there's this fraudulent transaction over here. This one is worth about $10,000, right? And what typically happens is that people have to manually go through the blockchain logs. You have to contact your IT team and to do further investigations, pull out the ledgers, and then try to make sense out of it. Here we have this whole user interface. We have actually already pre-processed the data to make it very easy for the front-end user to extract relevant insights out of it. So with this graph interface, you can simply import the neighbors of this address and see its neighboring connections. So one thing that stands out to me when I take a look at this transaction over here is that it's actually connected to another Bangkok hacker over here. So Bangkok hacker is actually another hack case that happened quite a long time back. But if you were to receive such a fund over here, you'd be very suspicious because this guy is also interacting with another suspicious entity over here. And you can easily see the how the timeline of the transaction goes. You can filter based on time, simple things like that. I think what's even more powerful is that we can cut short of all this process and simply query for the relevant information. So I think for example, in this one over here, we want to find information related to this transaction. So we can just import the relevant information. In this case, we're going to find a path from the hack wallet to this particular transaction hash. So we can just search a path. Here we found CryptoPay hacker. This was another popular hack that happened about a year ago, and we can actually trace it down to this one. Visualize different things over here. Okay, and this gives you a sense of the kind of tool we're developing, the kinds of information that we're trying to make available in a near real-time basis, and the scale of the data we're trying to process. The challenge, of course, in trying to make 300 million transaction ages and more than 100 million nodes readily available and calculate the precise transaction information that can be attributed to the different source. The main challenge over there is that it's actually a large graph computation problem. So even beyond the blockchain area or any area that we have transaction graphs, I think one of the challenges is how we can do it such that we are able to process and make use of the information as readily as possible. So this was one of the engineering challenges that we face, and it's going to be the subject of the rest of my talk. Okay, this is another graph visualization of a much smaller blockchain, Ripple. In this case, 1.4 million nodes, 2.6 million ages. It looks very nice with all the colors of the communities and stuff like that. But actually, how do you actually try to interpret and make sense of it? That's a totally different issue. And to do that, actually, the key is to pre-calculate certain information. When we deal with large graphs, I think one of the main questions why it takes such a long time to calculate, why we can't use typical methods, is that we normally find it to be challenging to simply do a sampling of the graph, because the graph normally is more meaningful as a whole rather than just the sum of its parts or the sum of its neighbors. Even generating summary stats is a challenge, especially when you want to generate it over 300 million ages and things like that. Visualizing is a challenge, which we try to solve with the Lynx product. And normally we are not only concerned just with a node or an edge. We also want to have additional relevant information on it, such as the wallet holding address, the total number of funds it's holding, information about the edge, time information or time dimension is really important, especially when you're dealing with large financial transaction graphs. And there is uncertain or data quality issues when we are not very sure about the quality of data we are receiving, and it's only eventually consistent after a certain point of time. So we try to deal with all these problems in our particular solution over here. We also want it to be scalable and it needs to satisfy or needs to try to minimize resource requirements as much as possible. Especially for current enterprise people who have database systems, I think a lot of them don't support graph operations. So this makes it even more challenging. Like, how can we make use of our existing infrastructure and database system to do this graph analysis? So I shall outline the approach over here. Actually, our BlockLynx product is built on Google Cloud Platform, I think, and this also allows us to achieve greater economies of scales and tap on various nice properties of cloud serverless functions to actually host it and deploy it at a very low cost. So let me give you an overview of the problem again. Here we are concerned with how we can pass on information, like node propagation, on a transaction graph. There are many use cases for node propagation, one of which is what I outlined over here, is pre-computing certain relations between entities. It has also been used for community detection via a label propagation approach, or semi-supervised tagging if you want to find out what's the missing value in particular entities. So this is something that we have applied in, for example, a large telco in Indonesia to try to identify the age and gender attributes of a lot of its customers, because sometimes the data that we collect is not really that complete or that accurate. So we want to use machine learning methods to improve it. So one thing we can do is these problems all fall under the category of node propagation. So again, more information about my data set. It's a sparse transaction graph, about 100 million nodes, 300 million edges, and it's growing rapidly. There's a heavily skewed degree distribution. So degree distribution is like the number of transactions between the nodes. You can think of it how connected the node is. So less than 10% of nodes are actually involved in about 80% of the transactions. And really, time order really matters, especially when we're dealing with this kind of fraud cases, cybersecurity, financial transactions. We don't want to inaccurately tag a person who interacted with exchange before the exchange actually got hacked. So this is really a key consideration for us in this problem. So here's how it looks like. We simply have a data set of vertex with different attributes and age with different attributes. The important thing is that it includes both a timestamp as well as the value that we want to propagate. And we want the solution to really scale into billions of nodes and billions of edges. We need exact information to be calculated across all nodes and edges. We are not only concerned with the largest entity, but if a business unit comes to us with a particular question on any random transaction hash or any address, we need to have information about it instantly. It should be fast enough to try out different parameters and settings. I think this one is really underestimated in a lot of these business settings. You try to create a solution and you deploy it once, but if the solution takes more than 24 hours to actually calculate and deploy, this means that you lose a lot of possibility in trying to experiment with different parameters and finding out what could potentially be a better solution. Yes, real-time updates. So this is another key part of the thing that we want to achieve with the BlockLynx product, and I think we managed to build it in. And we want to minimize costs as well. Okay, so here's how we approach it. Yes, on this diagram over here. So this diagram over here is like a side note actually, but it showcases some of the interesting things we found about as we explored the blockchain. So this is an example of a mixer component. The interesting thing about mixers in the blockchain is that actually they are all connected to each other, and they support multiple inputs and multiple output addresses. So we use a graph algorithm to pull out the entire component of mixers. Right. This is just an outline of the approach that we took. I will not go into too much details. Just highlight the main considerations we took as we develop our solution, and how we managed to make it at least 10 times faster and 10 times cheaper than the initial one. So like most enterprise, I think we have our own Spark Hadoop system, and one might think that it's a great way to use our existing Spark Hadoop system to implement parallel processing. After all, what we just need to do is scale, is just to loop across all the blockchain transactions, and this will sort of guarantee scalability. We actually tried this out, and we found that it took more than 2 days for us to do the entire propagation routine across the 300 million edges. We also require an extremely large machine. So for that, how large a machine is, probably a machine larger than 256 GB RAM. So that's more than a 256 GB RAM cluster. So that's really pretty expensive. What we learned from this is that sometimes it's better to find the right tools for the right job, and we can come up with a solution that is much faster and much cheaper than what can be done using Spark. So that's when we came out. That's when we came up with the inspiration to build our own product around. So another popular approach is to take one of the existing libraries out there. You might have heard of NetworkX. So NetworkX is a common Python library used for graph analysis. It has nice visualizations, a really nice to use API. It's very easy to compute summary stats, good documentation. But don't try out large data because it's really, really slow. It's going to hog memory, and it's going to be very tricky to deal with time series data. So you have a big data problem. Generally, I recommend to skip NetworkX and look at more performant graph libraries. But the problem with more performant graph libraries is that it's still not fast enough for a problem, though it's much faster than NetworkX. A lot of these graph libraries don't support like time series indexing out of the box. It's still very heavily memory intensive. So what we need is really a customized solution to build for this particular problem. And you might ask, why don't we use graph databases? So you might have heard of things like Neo4j and other graph database technologies. So we did consider them as well. But I think there's just too much overhead associated with like a graph database technology. Normally there is all these network IP connections that you take care of, and the time taken to pass information across like the intranet is much longer than it takes within your own computer. So I recommend just building it within a particular machine. So our methodology over here involves developing our own customized algorithm to make the best use of our own SQL system, as well as to develop a system that will be low memory usage, high performance, and scalable. So let's consider the problem in a little more detail and sort of lead you to where we're going with the solution. So for every transaction, a node propagation algorithm basically says, for every transaction, we just need to look up a vertex attribute, do a calculation based on the attribute, and maybe interact it with certain kinds of age attributes such as the value, and persist this information, because this is what we want to know, like what is the end state of the outcome after we do the calculation, right? And we repeat it. So if it sounds familiar, it probably is, because that's just a simple loop. The problem with our initial approach doing a loop is that we often find that we have to look up various values about a particular address, look up various values about a transaction. But actually, a lot of these can be calculated at the SQL stack. So this is a simple outline of how we try to optimize the entire thing. We skip the vertex table, and we just concentrate on the age table. So here we pre-merge the vertex attributes to the edges using our SQL system, and before we start the entire looping thing. Right, so it's really just pre-sort the data, stream it over, loop it in time order. It's really, really, really very fast. You remove 2 key value lookups at the very least. And there's negligible memory footprint because we do not need to store any transaction information. We just need to loop through the rows. And the question here is, can we even do better? Actually, we can. Now let's look at the second objective of trying to minimize cost and develop a solution for that. So this is where we combine our graph findings together with our current loop approach to try to get a better, more efficient solution. Okay, so in this first chart again, I present to you the degree distribution of the transaction graphs. This means how many connections each particular node or address has. What we see is that the blue bar shows the number of addresses, and more than 100 million addresses makes fewer than 10 transactions, right? And this consists of the overall consists of a small percentage of the total transactions. Rather, there are, for example, in the more than 10 million transactions, there are just two addresses that are responsible for about 40 million transactions. This is something we observe very common in the transaction graphs, where we see like key players that are responsible for most of the financial transactions that are happening on the chain. So that's the first thing. And with this degree distribution insight, what we learn from this is that maybe there isn't a need to treat each node or each address equally. We should give higher priority to the people with very high degrees, right? Because these are the key ones that we will always see in the transaction records. Now let's combine it with the second graph insight. So this one over here shows cohort like retention analysis. So let me explain it in a bit more detail. So let's take we take 3 cohorts over here: the January cohort, the February cohort in orange, and the March cohort in March. And we keep the customers constant for each cohort and look at how they decay over time. So what we observe is that the decay rates of the various cohorts follow very predictable patterns, follow very similar patterns. And if you calculate the percentage of it, it normally drops off by 85% month on month, and then a slight 5% decline, and sort of remains constant. So this means that our cohort retention analysis sort of tells us like the order of the markup property we're looking at, and from there we can derive additional optimization to make our transaction analysis even more performant. Yeah. So the question of what's the catch? The catch is actually it can be used to inform the size of the cache. The cache being CHE, the memory cache. So that's where we're going next with what we're doing over here. So the loop approach V2, our current implementation, we do not need to store any data in memory. We have a slightly poor performance, but we can hold the intermediate state in like a key value store. So we just leverage on the graph degree distribution findings and the fact that active accounts at time t are more likely to be active in time t+1 following the decay rule. And we use the size of the decay or the number of the fact that all participants are normally active for about a month to identify the size of cache. So this means that we use a least recently used cache with the size given by about a month of worth of activity. So what are the pros of using this approach? It's really fast. It has almost negligible memory footprint and it's cheap. Because here we subsidize the memory use for like a SSD, which is used to hold the key value, a persistent key value store. So it's really fast, really performant, and we are able to scale our transaction analysis across more than 300 million transaction pages. We are able to tag as many categories as you possibly can need, as you possibly want. So this makes it very powerful for tracing entities on the blockchain or any kinds of financial transaction graphs. So this is our final product over here at BlockLynx. You can take a look at the blocklynx.cylynx.io if you want to actually do a demo of it. So here are some takeaways that we came about after dealing with the problem. I think after spending a large time in like transaction graph analysis, really the key is to start with like the summary statistics and explore what are the characteristics of the graph we are looking at. And for that, I'll skip network X and start working with more performant graph libraries. Our existing solutions actually can do a lot of useful things. And for example, if you have an SQL system already, we can do certain kinds of optimizations and pre-compute certain results that SQL systems are very good at doing batch computations, and help us stream these results to a compute machine in order to make our solution even more performant than any in-memory kind of system that you might have. Really. And really, there's still further room to optimize, but for this particular problem, we found it unnecessary. I think we can eventually bring our time down by another like 25% easily. So that's sort of the gist of my talk. I think there are many things that we are still trying to explore. We still have not solved, especially with regards to how we can visualize large transaction graphs effectively, how we can make these insights readily available and make it useful for the different business units, enterprise teams, for regulators, for exchanges, for financial institutions, for any kinds of blockchain projects you might have. So this is something that we are actively researching on. I think part of it, of the solution you can see, is our BlockLynx Investigative Explorer that I demoed earlier. But that's only like I think 20% of where we are going with the entire solution. There are a lot of challenges on distributed graph computing. Some of it we are also looking to solve. Monitoring the performance, we try to take that into account with our product. So this sort of makes, for our product, there's no need for additional monitoring requirements. All these are taken care into account when we deploy it into the Google Cloud platform. And I think another interesting thing is like how we can try to make graph databases and different graph computation software work seamlessly together. I believe we have sort of made progress on that front, but there is a lot more that can be done. So if you're using any graph database or any other graph libraries and would like to collaborate with us on the various challenges out there of visualizing data, making more performance calculations, feel free to reach out after the talk. But otherwise, I think the only thing I would have to say is feel free to test out our blog Lynx demo over here. It's free to test and free to try out on the Ethereum platform.